Assalamualaikum warahmatullahi wabarakatuh. Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. Our event today is about to begin. Let me remind you to turn on your camera and use the virtual background that's available in the comment box. Let me introduce myself. I am Rizka Lestari, as the MC for our first event in the entire series on World Class Professor Events 2023. And on behalf of the organizing committee, we express our appreciation for all the participants present today. Today's event is first webinar series, and we will discuss about a perspective on the fabrication of heterogeneous photocatalysts for enhanced hydrogen production. Before we start to talk about it, let me read our schedule for today. Our agenda today will be start with opening remark from the Director of Institut Teknologi Kalimantan, and it will be continue with greetings from our host of World Class Professor 2023, Dr. Lucy Ernawati. After that, we will also have a speech from our invited World Class Professor, Professor Hisao Yoshida from Kyoto University, and directly continue in the presentation session from our three special speakers, Prof. Hisao Yoshida, Prof. Muhammad Mansub Khan, and Dr. Osi Arutanti. And then there is a question and answer session at the last time after presentation. For the beginning, we will take picture together because the number of slides of participants in the online room is 3 slides. Then the photo will be taken 3 times. I will be driving the photo session now. We will start from the first slide. 1, 2, 3. Okay, the second slide. 1, 2, 3. And then the last slide. 1, 2, 3. Okay, thank you everyone. For first schedule, we will have an opening remark from our Rector of Institut Teknologi Kalimantan, Prof. Agus Rubianto. Please welcome Prof. Agus, the time is yours.
Your Honorable Professor Hisao Yoshida has invited class professor program from Kyoto University. Good morning. Your Honorable Muhammad Mansub Khan as guest speaker from University of Brunei Darussalam. Your Honorable Dr. Eng Osi Arutanti as guest speaker, as well as a research from National Research and Innovative Agency. Dear participants, ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Selamat pagi, good morning, Ohio. I have the great pleasure today, this favorable opportunity, the design for cooperation in the framework of LPDP. Therefore, it is great honor for me to speak the delegation of the class professor 2023. On behalf of Rector ITK, first of all, I would like to say thanks for all the committee of the World Class Professor 2023. They worked so hard to prepare to this event so that it can take place well. And I would like to thank for all the speakers at today's event who are willing to provide the knowledge and research experience to be shared with all participants. Today, we have only met online, but maybe one day, hopefully, there will be an opportunity to meet in a person and discuss further about research cooperation with Institut Teknologi Kalimantan. Let me first introduce ITK to everyone. ITK is a university that focuses on science and technology, and our vision is to become an institution that excels and plays an active role in the national development. So we'll be continue to improve ourselves in various aspects. There are 22 study programs and 5 faculties. The number of students is 5,700. The number of lecturers is 247. The academic staff is 120. We have alumni almost 2,157. ITK students come from various regions. Thanks that ITK's location in the center of Indonesia. There are 2 integrated laboratories, 250 collaboration with government, education, and private institutions. This year, in the 3rd year, ITK has the opportunity to be one of the hosts in the world-class professor event. Thanks to Dr. Engineering Lucy Ernawati from the Chemical Engineering Department, who is the host for today's event. Because she has always tried to fight for ITK to be given the opportunity for this valuable world-class professor event in these years. Today, we have 3 speakers from 3 different institutions, namely Professor Hisao Yoshi as invited world-class professor, program 2023 from Kyoto University, Professor Muhammad Mansub Khan as guest speaker from University Brunei Darussalam, and Dr. Eng Osi Arutanti as guest speaker, as well as researcher from National Research and Innovation Agency. All speakers, ladies and gentlemen, have tremendous experience in the field of research. So I hope that all participants can absorb knowledge presented well and can be inspired to come up with innovative research to support the progress of Indonesian research. So, I respectfully open the World-Class Professor 2023 event success and good luck. I apologize for not being able to attend the seminar as whole due to the activities. Thank you very much for your kind attention. Arigatou gozaimasu. Terima kasih atas perhatian. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Terima kasih banyak Pak Agus. Thank you very much.
Thank you, Prof. Agus. And we will continue with speech from Dr. Lucy Ernawati as our host of a world-class professor today. Please welcome Dr. Lucy.
Okay, thank you, Miss Rizka Lestari. Assalamualaikum warahmatullahi wabarakatuh. Good morning of the participants. Honorable mention, Rektor Kalimantan Institute of Teknologi, Prof. Agus Rubianto, for giving the opening remark. Honorable mention, our outstanding speakers. On behalf of the host of this event, I welcome every one of you it is give us a great pleasure to welcome you to our first virtual event of World Class Professor Program this year. We appreciate your carving out times despite your busy schedule to attend this agenda. Gratefully acknowledge toward to Indonesian Endowment Fund for Education (LPDP) and Ministry of Higher Education, Culture, Research and Technology Republic Indonesia for financial support on this world-class professor program. I also appreciate to the world-class professor management teams for their a lot of hard work was put to ensure this event can be held. Today, we have a discussion on a perspective on the fabrication of heterogeneous product catalysts for enhanced hydrogen production. And we have here with us outstanding speakers and professionals in their respective fields that will be taking us on the presentation lineup for this webinar today. Our invited world-class professor for Professor Hisao Hoshida from Kyoto University, Ohayo gozaimasu sensei, and warm welcome. Our second speaker, Professor Muhammad Mansuk Khan from University Brunei Darussalam. Good morning, Prof. Mansuk. And our third speaker, Dr. Osi Arutanti from Research Center for Chemistry, National Research and Innovation Agency. Good morning, Dr. Osi. I hope their presentation will also be made available for all registered participants, and I hope you'll find it is informative and engaging. Mr. Ginting will serve as a moderator to oversee and facilitate all decisions in these meetings today. So please kindly mute your devices while the facilitator is speaking so that others will not be distracted. Thank you once again for joining us and enjoy our virtual events today. Thank you all.
Thank you very much, Dr. Lucy. Without further ado, we will start our program, who will be guided by our moderator, Mr. Rizky Ramadana Ginting. Mr. Ginting is one of our lecturers on Chemical Engineering Department in Institut Teknologi Kalimantan. Please welcome Mr. Ginting. The time is yours.
Okay, thank you very much, Mrs. Rizka. Good morning, everyone. Welcome to the World Class Professor Series of 2023. My name is Rizky Ramadana Ginting from Institut Teknologi Kalimantan, especially from Chemical Engineering Department. It is my honor to be your moderator today. Our highest appreciation goes to the Rector of ITK, Prof. Agus Rubianto, and then Prof. Hisao Yoshida as invited world-class professor from Kyoto University, Prof. Mansuk from University Brunei Darussalam, and Dr. Osi Arutanti from BRIN. Thank you for your presence today and to all of the participants. Earlier, we have received an opening remarks from Prof. Agus Rubianto and greetings from Dr. Lucy. And now we will start with the main event of the discussion. Today, we will talk about a perspective on fabrication of heterogeneous photocatalysts for enhanced hydrogen production. We hope that today's topic can give an insight regarding enhanced hydrogen production and how it can benefit the general society and scientific community. The discussion will start with 30 minutes presentation from Prof. Yoshida and then continued by Prof. Mansuk, and the last speaker is Dr. Osi. After that, we will have 45 minutes Q&A session. During the presentation, if you have any question, you can write it in the comment section, or you can raise your hand during the Q&A session. We will start with the first speaker, Prof. Hisao Yoshida from Division of Material Science, Graduate School of Human and Environmental Studies, Kyoto University. Before we start, I will read a short introduction of Prof. Yoshida. Prof. Yoshida received his Master and PhD from Kyoto University. On year 2000, he received a Catalysis Congress Prize of the International Association of Catalysis Society. On year 2003, he received a prize for Young Scientist of Catalysis Society of Japan. Good morning, Sensei, Prof. Yoshida.
Good morning. Can you hear me?
I hope you are well, Prof. Today, we will start with 30 minutes presentation from you, Prof. Maybe you can start now. The time is yours.
I will share. Is it okay?
It can be clear, Sensei. It's fine.
So, thank you very much and quite kind introduction. My name is Sao Yoshida from Kyoto University in Japan. Today, I will present our works about the photocatalytic and photothermal reforming of methane for hydrogen production. This is quite a unique study to form the hydrogen. The talk divided into 5 parts. First, I would like to start the introduction. It's my profile. So now I am studying in Kyoto, but before that I studied in Nagoya University, also in Japan. But throughout my career, I always studied catalysis and photocatalysis. Now I am concentrated to study photocatalyst mainly. Then this is a Kyoto map. Not so far, but a little bit far from Indonesia. And you may see in Kyoto the beautiful shrine and temples, and also the famous Kyoto University. My laboratory has four subjects about photocatalytic and photothermal catalysis. Today, I will talk about the photocatalytic methane conversion and the photothermal conversion, about half of my laboratory topics. As you know, methane is a very important hydrogen source. Now we produce hydrogen in industry by using the methane as a source. Here are famous reactions of methane famous reactions that we studied. One is the methane coupling to produce the ethane and the hydrogen. The second is the dry reforming. In this case, the methane with CO2 gives carbon monoxide and hydrogen. And the third is the methane and water react together to produce a carbon dioxide and hydrogen. The last one is the main route to produce a hydrogen in this moment in the world. As you can notice, to produce the hydrogen, unfortunately, we must produce CO2 also. However, this process is quite efficient, so that industry select this one. And these kind of reactions need a huge energy to promote, to go to the products. Here, I show the Gibbs energy of these reactions. These values is very high to operate at the room temperature, so that we need usually at high temperature to operate them. But we studied by using the photocatalyst for these reactions, and then we success to promote the reaction. Unfortunately, the reaction rate is still low, but we are trying to increase it. Today, I will talk about the photocatalysis. Maybe you know well. In this case, photo energy converted to electron and hole in the semiconductor photocatalyst. And on the surface, reductive and oxidative reactions occur. On the other hand, the photothermal catalysis, in this case, photon into the metal nanoparticles, because you know the metal particles usually black colors in the catalyst. So this photoabsorption gives huge heat, so that the catalyst itself was warmed by the light, and then the catalytic reaction occurs. It's also a quite clever way to use the solar light. So I will talk these two methods. First, photocatalytic reaction, photocatalytic steam reforming of methane. Here, I demonstrate the water splitting by using the calcium titanate with platinum co-catalyst. In this case, we flow the water vapor into the photocatalyst, and we can confirm the hydrogen oxygen as a product. It's also very clever method to get the hydrogen. But if we add the methane into the system, the efficiency jumped up to promote to produce a hydrogen and the CO2. So in this case, in this reactor, the methane steam reaction reforming is promoted to produce a hydrogen, and also water splitting occurs. Now we are concentrate to do the methane reforming. Here we developed some catalysts, and this is one of the most active one. The catalyst is tantalum, sodium tantalum with lanthanum doping, and we load the platinum co-catalyst on it, and the reaction occur very stably. This is the production rate of the hydrogen and the carbon dioxide. It continuously produce the hydrogen and carbon dioxide in this reaction scheme. So that is our first success to promote this one. And after that, we developed some catalysts in this way. Today, I want to deliver the story of the reaction mechanism study. Here, the same graph by using the titanium oxide with platinum co-catalyst. In this case, it's active. However, we found the interesting phenomena on the surface of the catalyst. Something accumulated. The color is brown. So we wanted to know what is this. Then we operate the reaction conditions. First, the methane and water was flowed into the reactor, and we switch. In this case, we can see the color at the end. And after that, we cut the methane. I mean, the water, only water was introduced. In this case, the color was removed into the initial state. And however, in this case, also we observe the products, hydrogen and carbon dioxide, so that we think this brown color is intermediate in this reaction. So on this result, we summarize the proposed mechanism. First, on the surface of the catalyst, water and methane was oxidized to make the intermediate. After that, and the water also additionally oxidized to form the OH radicals, and then the OH radicals attack to the intermediates to form the CO2, and on the platinum side, on the titanium oxide, proton are reduced to hydrogen, so that we get the 4 times hydrogen to carbon dioxide in this system by photocatalysis. The second, I want to introduce the co-catalyst effect. For example, in these reactions, we usually use the platinum. So I also use the platinum for the next photocatalyst, potassium titanate. In this case, the reaction was promoted, however, a little bit decreasing with time, and byproduct carbon monoxide also was formed. Then we changed the co-catalyst to the rhodium. The reaction rate became higher, and the byproduct was not observed. Then we change the loading method of the rhodium on potassium titanate. In this case, we found photo deposition is quite effective for this reaction. And we observed the surface by using the microscopy. In this case, we found some species of rhodium, and in the good sample, we found 2 types of the co-catalysts were loaded on the surface. Then the size is quite different, and morphology is also different. So that we concluded before that we confirm the state of the co-catalyst by using the EXAFs to know the local structure of the rhodium. In this case, the best catalyst has 2 types of the rhodium, and we concluded that this is a band energy diagram, and photocatalyst is here, and co-catalyst is here. Rhodium metals can receive the electron from the photocatalyst to promote the reduction reaction, and rhodium oxide on the surface, a little bit larger particles can receive the holes from the photocatalyst to promote the oxidative reactions, to promote to oxidize the methane and the water, and totally the efficiency of the photocatalyst was improved. Third, the photothermal DRM. DRM means the dry reforming methane. In this case, photothermal. It means a little bit different from the photocatalyst. This is a report of us 2020, and then to this year, the reaction is here. It's also very difficult reaction at a room temperature. In this system, light absorption was occurred to heat the metal nanoparticles, and then reaction occurs on the metal catalyst. In this case, not photocatalyst, but catalyst, metal catalyst. Then, photothermal reaction has 2 types or more. One is a photo-assisted thermal catalyst. In this case, catalyst was warmed by the heater as usual, and add the photo energy. This is a photo-assisted thermal catalyst. And ours is a photothermal catalyst without heater, just light. I mean, we want to use the solar light in future, so we use only the light. and IR thermometer monitor the temperature of the catalyst. Here the result and the time course of the reaction. We can obtain the carbon monoxide hydrogen as a product in the DRM reaction continuously. So we successfully obtained the good system. And to know the reaction temperature, we observed the exhaust technique. I would like to show the principle of the exhaust oscillation here, but very difficult. I will skip to tell the details. However, fully transformed exhaust gives the clear peak. It is due to the rhodium shells. It depends. The intensity depends on the temperature. So we can calculate the temperature from that spectrum change. So by using this one, we operate the exhaust measurement in this operand system. The visible light and the near infrared is here to the samples. This is using for the photothermal reaction. So that I mean we operate the exhaust measurements in situ. So we can find the temperature of the catalyst. Here, this is the time course, and upper is the temperature. Then, when we switch on the light, the temperature of the catalyst increase immediately. At that time, we flow the carbon dioxide and the methane into the reactor so that we can obtain the product at the same time. Here, the result, the carbon monoxide, hydrogen come out. It means the high temperature gives the activates the metal catalyst, and the metal catalyst gives the products as a CO and hydrogen. The IR DRM gives the equivalent molar of the carbon monoxide and hydrogen. However, the next reaction, CO2 plus hydrogen, also occurs to promote carbon monoxide formation, so that a little bit the carbon monoxide is higher than the hydrogen. However, anyway, in this system, we can warm the catalyst by the photo energy. There are another type of the photothermal SRM also present here. This reaction also difficult, but important is the oxidant is water instead of CO2 here. This is a system, that's similar system. Then we compare always we compare with the thermal catalyst. Then this is a traditional implementation method to use the catalyst, and we prepare the 4 samples by using the different precursors to obtain the nickel catalyst. Here the result, 4 types of catalysts can work as well, and we monitored the catalyst temperature, surface temperature, about 800. So this is a photothermal reaction. And the right hand side, it is in dark. I mean, just heat the catalyst. Of course, these catalysts provide the product as well. And because when we increase the temperature, the similar temperature, so instead of the heat, we can use the photo energy here. So when we increase the light power, the temperature increase, and also the hot catalysis also increase. Then, for example, this condition gives the hydrogen and carbon monoxide, carbon dioxide and monoxide as a product continuously. It means this system is successfully produced hydrogen by using the photo energies. So I would like to summarize my talk. Here, I presented the photocatalytic and photothermal reforming of methane for hydrogen production. So photocatalysis can promote both SRM and DRM by using methane. And the second part is the photothermal catalysis can promote them and more efficiently. I skipped the values, but the reaction rate is very fast compared to the photocatalysis, unfortunately. So then, for photocatalysis should be applied for other reactions like this: water decomposition, carbon dioxide with water, or new reactions, or water purification, or metal recovery. This is based on the catalytic of the catalysis, so it's quite promising field. In this case, in the present case, the methane reforming. Methane reforming means the methane the hydrogen source, and also we use the oxidant like carbon dioxide or water. In this case, photothermal reaction also works, and the efficiency higher. It is acknowledged for my students and the professors and the financial support. Thank you very much.
Thank you very much for the speech, Prof. Yoshida. So the earlier Prof. Yoshida gave us the presentation about catalytic methane conversion for hydrogen production. We will keep all questions till the end of the session. So if you have a question for Prof. Yoshida, please put it in the comment section or raise your hand during the question and answer section. Terima kasih. Thank you, Prof. Yoshida.
Thank you.
Okay, we move on to the next presenter, Prof. Mansub from University Brunei Darussalam. Prof. Mansub is a professor of inorganic chemistry and nanotechnology at Chemical Sciences, Faculty of Science, University Brunei Darussalam. He has earned his PhD from Aligarh Muslim University, India in 2002. He has worked in India, Ethiopia, Oman, and South Korea, and has established excellence in teaching and novel research. He used to teach various courses at undergraduate and postgraduate levels. He also has edited 3 books and authored 2 books. Good morning, Prof. Mansub.
Yep. Thank you, Mr. Rizky, for a kind introduction.
Okay,
So first
Prof.
of all, I would like to say Assalamu alaikum and good morning to everyone.
Waalaikumsalam warahmatullahi wabarakatuh.
I would like to thank you, Dr. Lucy, and the other members for your kind invitation for this world-class professor program. So let me share this slide first. Your slide is clear to everyone?
It is good, Prof.
Slide is okay?
It's okay, it's okay.
Yeah, how about my voice?
It's okay, it's
Okay.
clear.
So, Bismillah. So based on the theme that I have received from Dr. Lucy, a perspective on fabrication of heterogeneous photocatalyst for enhanced hydrogen production. So for today's talk, I have chosen a very general and broad topic, especially for the beginners. So what I have come to know that at the Kalimantan Institute of Technology, I mean, you're starting the photocatalyst very recently. So that's why I have chosen very fundamental topic and very general, so that the beginners, especially the students, can be benefited. So here I have chosen the nanomaterials for photocatalysis. So contents of my talk, my brief introduction, already Dr. Rizki already has given my introduction, but I'll give a very brief introduction because it is already in the slide. I'll just pass it over. Then introduction of the University of Darussalam, where currently I'm working. The nanomaterials for photocatalysis, that is the main part of my talk. It will include the fundamental of photocatalysis, designing photocatalyst, application of photocatalysts, and all will be general. I'm not going to talk any of very specific things. It will be general so that the majority or the beginners can be benefited. Then finally, summary and acknowledgement. So if you see my research area, this is the my research area where I'm working on the green synthesis of metal nanoparticles, metal oxides, chalcogenides, inorganic nanohybrid materials, as well as their nanocomposites. Band gap engineering of metal oxides, chalcogenides, synthesis of binary, ternary, quaternary composites, then the other synthesis of graphene and graphite nitride the materials and their composite material, and also trying to develop some novel and smart nanomaterials for visible light harvesting. Apart from that, I'm using these materials for different type of photocatalytic reactions, hydrogen production, water splitting, sensor, optoelectronic devices, photovoltaics, electrode materials, and all. Apart from that, I mean, in general, we can say that I'm using for the environmental remediation, and also I've used these materials in the microbial fuel cells. Apart from that, some of the material I'm also using for some biological activities, especially if you'll see here the antioxidant, and we have introduced the photo-antioxidants. Antibacterial is very common. We have introduced the new concept, the photo-antibacterial, and the wound healing cosmetics creams and all. This is the research area where I'm working material science and material chemistry, materials for energy, environment, and biological, band gap engineering. And regarding the publication, I have about 200 publications and book chapters, about 23 book chapters, some patents, and I have edited 3 books. 2 books I have contributed as an author. And my Google Scholar citation is about 12,000, and Scopus citation is about 10,000 citations. So these are the edited books that is published by the Springer and Elsevier. And this is the authored book, and this one is the latest book, and it is theoretical concepts of photocatalysis. Those who are interested, want to learn the fundamentals of photocatalysis, please consult this book. Okay. Hopefully you can get in your library, or I'll ask Dr. Lucy and others to recommend to your library. So yeah, so this is the University of Darussalam where currently I'm working. I joined here in 2015, and since that I'm continuing here. So you can see the Brunei is a very small country. It is located here. That is close to the Miri and Indonesia, and this is about the university ranking and all. So I'm now coming to the main topic: nanomaterials for photocatalysis. So as I told you in the very beginning that I'm going to discuss a very fundamental and general view. I'm not going to discuss any particular material, very general, so that the beginners can understand. So this is the nanomaterial that we need for photocatalysis. And if you see the photocatalysis, what happens here? We need the light. Light is the one requirement, and we need the material. Okay. And if you irradiate the material with the light, what will happen? There's a formation of hole and electron. So that is the beauty of this photocatalysis. It's very simple, and we call it green approach because here we don't have any side product or harmless product that is affecting the environment. So we try to utilize this hole and proton, and using this we come up with different applications. So if you can see here, this is the material, and with the irradiate with the light, depends on the light, what type of light you want to use, and what type of application you want to do. You will irradiate, you will get the hole and the electron. That is the main concept here. And then using this electron, we can do many reduction reactions, and using this hole, we can do many oxidation reactions. So moving further, sorry. So I'm now going to discuss the photocatalysis first and then the photocatalyst. So historical development, fundamental of photocatalysis, principle of photocatalysis, general mechanism for photocatalysis, factors affecting the photocatalysis, then design of photocatalysis and all, and then examples of some photocatalysis, ideal criteria for photocatalysis, and then the strategies. What are the strategies that we should follow so that we can increase the efficiency of the photocatalytic reactions? So this is the general you can say the figure that shows that how the photocatalysis has started developing from long back, from 1960 until the current year. Okay, so if you see the fundamentals of photocatalysis is a type of catalytic reaction that is influenced by the type of light and the photocatalyst used. So it depends what type of light that you are going to use, whether you are going to use the UV light or visible light or any other type of light. And then the catalysts, because all the catalysts are not same. We have the metal oxides, you have the chalcogenides, you have the composite and different type of composites. So it depends on that. It is a reaction that uses a suitable light to activate the photocatalyst, which enhances the rate of a chemical reaction without being used up. So photocatalysis is, sorry, is motivated by natural photosynthesis. You will see the natural photosynthesis. In photosynthesis, what happens? We have the plant or leaf, there's the chlorophyll, and it absorbs the sunlight, and then it utilizes the carbon dioxide and water, then it produces the glucose, starch, and all carbohydrates plus oxygen. In photocatalysis, what happened? We have the material. So there is a similarity between the chlorophyll and the material here. So this is the material, it absorbs the sunlight, and then it produces electron and holes, and using these two, it produces the free radicals, and that degraded, or it depends on what type of application you want to do. And finally, you will get the harmless end product, that is the water and the carbon dioxide. Okay, so that is the beauty of the photocatalysis. That's why we call it, it's a green approach. So, however, on the contrary, photocatalysis form or generates electron and holes. So this is very important here, which helps in the formation of free radicals, which are strong oxidizing and reducing agents. So these free radicals used for the decomposition of the pollutants to carbon dioxide or the water in the presence of photocatalyst. So you can see here, these figures here using this electron and hole, we do different reduction and oxidation reactions here. So you can see here at the conduction band, reduction reaction takes place. At the valence band, the oxidation reaction takes place. So photocatalysis process predominantly revolves around following five pivotal steps. Light absorption. You can see here, the first thing that the material should absorb the light. If material is not responding to the light, we cannot call it a photocatalytic reaction. It will be a normal catalytic reaction. So the first requirement is that we should develop a material that can absorb the light. Now the question is that which light, whether the UV light or the visible light or NIR or IR. So based on your requirement, you can design the material. So light absorption or harvesting, excitation and exciton or charge separation here, that is very important. There must be excitation, then charge separation, then charge separation transfer. The charge must be transferred, otherwise it will recombine and the efficiency of the system will be very low. So charge recombination, oxidation reduction processes and all that will take place here, and desorption of reaction products from the catalyst surface or reaction medium, and finally mineralization of the end product. So these are some of the stuff that is common, that is the very fundamental of the photocatalysis. So you can see this is any semiconductor. We have the valence band and the conduction band here. This is the band gap energy. Based on the band gap energy, it can absorb the light. It depends on the material and all. If you radiate the material, the hole and electrons will be formed here. The electron will get excited, move here, holes will be formed here. And then here, the reduction side, and this is the oxidation side. Okay, and then if charge will not move or it will not get migrated, recombination will take place. So we have to make these charges, somehow we have to move it or migrate it. And then using these free radicals, we can do many other reactions here. So again, the similar figure, but with a very complete here, you can see here it can absorb the light, and then there is excitation of the electrons, there's formation of the hole and the electrons, and at the surface, different reaction takes place. So that is the beauty of the photocatalytic reaction. Either you can utilize the electron here directly and the hole, or in the primary reaction or in the secondary reaction, where the free radicals, it can combine with any organic compounds or other inorganic compound, and then subsequent reaction can take place. So you can see here, this reaction here, this is the primary reaction, and this is the secondary reaction where the free radicals are used here. So again, here you can see this is the material here. It will absorb the light, and the electron and holes will be formed. The water can react with the hole, it can form the free radicals. In the same way, oxygen, it can react with the electron, and superoxide radical can be formed, and these can be utilized for the respective reduction or oxidation reaction, or we call it for the secondary reactions. Yeah, so you can see here, this is any semiconductor, it can absorb the light, and the excitation of electron will take place, hole and electron will be formed, oxygen can combine, you can get the free radicals here. This is the primary reaction can take place using the hole or the electron, and then the secondary reaction can take place, this one. So this is the principal thing about the photocatalysis. So if you do any reaction, yeah, this is the very common thing. So factors, there are many factors that affect the photocatalytic reaction. So if you see, the temperature is one of them. If you vary the temperature, the photocatalytic reaction may be different. pH of the solution, light irradiation time, light intensity, source of light, what type of source you're using, then the concentration of the pollutant, the particle size that is related with the material. As you know, the nanochemistry is very fascinating, and it depends on the particle size. So here, particle size plays very important role. Amount of the photocatalyst that you are using here, the morphology, again, it is very important. So if the same material, for example, if you're using the titanium oxide, if it has a different morphology, the response will be different. So then the surface area, yeah. In catalysis, you know very well, the surface area plays very important role. So in the same way, in the photocatalytic reaction also, if you have a highly porous material that have high surface area, then hopefully the response will be better. So, and then the presence of electron acceptors, sometimes we use a different electron acceptors to accelerate the reactions, or to sometimes trap the different the free radicals for specific reactions. So photocatalysis, what is photocatalysis? It's a material. Time being, we're talking about the photocatalysis. So now the photocatalyst. Photocatalysis is a substance that participate in a chemical reaction without being consumed, which results in the change in the rate of the photoreaction. Photoreaction is a chemical reaction that involves the absorption of light by one or more reacting species. So, or in other words, a photocatalyst is a substance that can absorb a suitable light. That is important here. It depends in which part of the electromagnetic spectrum you want to work, whether you want to work with the UV light or you want to work with the visible light. That is important here, which helps in chemical transformation of the reactants by lowering the activation energy and repeatedly coming in contact with the intermediate chemical species, which helps to convert the reactants to final harmless end products. The physicochemical properties of the photocatalyst are crucial for its performance. So these properties and characteristics are usually established according to the nature of the photocatalyst. For example, what is the composition, size, shape, morphology, purity, defect. Defect is another very important thing. And the source of the material, how it was fabricated. Same material, if you use a different synthesis method, will have the different characteristic. For example, if you want to synthesize the titanium oxide or zinc oxide or any semiconductor, if you use a different material, for example, if you're using the hydrothermal or any other method, the material will acquire the different characteristics. So it depends on that. So example of the photocatalyst, you can see here, we have the different, the photocatalyst, the binary compounds, for example, the metal oxide, the chalcogenides, doped metal and chalcogenides. And then we have the ternary compounds, we have the quaternary compounds, and then the different type of nanocomposites and the defected materials. So we have the very big class or different classes of the photocatalyst material. Depending on your application, your suitability, you can choose the material and you can work on that. So ideal criteria of the photocatalyst. Usually an ideal photocatalyst should have some basic properties and characteristics such as it must be active under light, or UV light or visible light, NIR, IR, or it depends on that. So appropriate electronic band structure and band gap energy is very important. So it depends. Accordingly, you should have a appropriate band gap of the material, the range of energy level, and that contain electrons within, as well as the range of the energy that may have not. Okay, and then the precise band edge position. So if you'll see here, the materials, sometimes you will find that the some materials, they have the same band gap. For example, if you see the zinc oxide and the titanium oxide, their band gap is approximately same, that is about 3.2, but their bandage positions are different. So based on the application, you can choose the material for which application you are going to use. So when you are proposing any plan, if you have any plan, so you have to see what is the band gap of the material and what is the bandage position, because the application, it will depend on that, on the bandage position. So efficient light absorption or light harvesting ability to be able to excite electrons to the conduction band. The other important characteristic it must have should be non-toxic. The material what we choose, it should be non-toxic, low cost and easily availability. Only then we can do at the commercial scale. If the material is toxic, it will have many impact on the environment. And if it is expensive, for example, then the technology that it will come up, it will be very expensive and the commercialization will be very difficult. So band gap energy and bandage position, the same thing what I've discussed before. So when you're choosing the material or other material, you have to be very careful that for which application you are going to choose, whether you are going to choose only for the oxidation reaction or the reduction reaction, what is the oxidation potential, what will be the reactant. Based on that, we have to choose the material based on its band gap energy and the bandage position. So ideal criteria of the photocatalyst capable to generate charge carrier. That is very important. If you're using any material, if it cannot create the charge carrier, then it will be useless. So the capable to generate charge carriers when stimulated with the required type and amount of light energy. In other words, smaller band gap materials are more appropriate in general. Why? Because if the band gap is very large, then you need the very high energy like the UV light or even the stronger light. So if you have the material or the photocatalyst that has the narrow band, whose energy lies within the visible range, then you can use the visible light that is free. Favorable charge transport characteristic and high charge carrier mobility. So that is very, very important here. The material should have high charge carrier mobility so that you can reduce the recombination. So should not be susceptible to photocorrosion. The material should not get photocorroded because there are many material, especially the chalcogenides, they will get the photocorroded. So the material should have and the anti-photocorrosion. So this will cause a deviation, deactivation of the photocatalyst over time. So they should have property of chemical and biological robustness. Chemically stable in a variety of conditions. So stability is another factor here. Highly stable without changing the properties of the photocatalyst when various conditions are applied. So because sometimes we have very high temperature or acidic condition or other thing. So the material should be stable. Reusable, easily recover and reuse with no considerable decrease in the photocatalytic activity. So these are some of the criteria for the material, and the last one, non-toxic. Material must be non-toxic. So strategies for enhancement of the photocatalytic reaction. Sometimes what happens if you have the pure material, sometimes it doesn't respond to very good reaction. So what we do, we have the different strategies. For example, here you can see the metal dopant. We use the different dopants. It can be the metal dopant, it can be the non-metal dopant, or we have the different heterojunctions. So using these strategies, you can come up with the more effective material. For example, the metal doping, we can use the different metals, maybe the transition metal or rare earth metal for the doping, and based on your material and your dopant, you can get the different the response of the material. As metal ions are incorporated into the lattice, impurity energy levels in the band gaps are formed. So you can see here the different energy levels will be formed that will help in the movement or the migration of the electron from valence band to the conduction band, as well as the migration of the charges. So metal ions act as an electron sink and help to reduce the charge recombination. Metal ions should be dropped near the surface of the catalyst particle for a better charge the transfer. In case of the deep dropping, metal ions likely behave as recombination centers since electron hole transferring to the interface is more difficult. Overall, effect of the adding dopants is band gap becomes lower and light absorption shifts to the visible spectral range. So that is important here, because if your material is a wide band gap, so it is very, very difficult because you have to work with the UV light that is harmful here. And similarly, you can use the non-metal doping. We can dop with the non-metal, and if you dop with the non-metal, especially the valence band will get affected or it will move upward based on the dopant here. So you can see here, we can use different non-metals, maybe the nitrogen or phosphorus or sulfur and all, and you can dop, and that will affect the valence band, and the band gap will be bit reduce, and excitation of the electron from valence band to visible band in the visible region is possible. Next one is metal loading. So if you see the metal loading is different than metal doping. In metal doping, what we do, we add the metal in the material, or you can say in the lattice. It goes to the lattice, and then it will affect the material in that way. But here in metal loading, what happens? We have the material or the metal oxides or chalcogenides, and then we modify the surface. So that is the metal loading here. So we can modify the photocatalyst using different metals. It depends on your application and all. So doing that, as the Fermi level of these noble metals are lower than that of the catalyst, photoexcited electrons can be transferred from Cb to metal particles deposited on the surface of the catalyst, while photogenerated Vb holes remain at the catalyst here. So this is the mechanism here. So this is the another strategy that we can do them by metal loading. Next one is the formation of the heterojunction or coupling. So if you have the different type of metal oxides or different type of material, you can take the advantage because the different materials have the different characteristics. So we can form the heterojunction materials, or we can couple two different materials. And using that, what we can do, the charge mobility or charge transfer will be faster, and we can reduce the recombination. So this is the another strategy that you can adopt here. And the next one is the defect formation. Sometimes, as I told before, that the pure materials are not very good, or I mean, good in the sense means the response that you are looking for. So what we do, we create some defect. So the introduction of defective metal oxides appears to be a promising approach for shifting the optical absorption edge to lower energies, thereby increasing the absorption in the visible region. So you can see here, we can form different type of defects. So the defects can be, maybe, for example, you can see the oxygen vacancy defect, or even the formation of the low valent ion. The defect in the metal oxide structures are caused mainly by the formation of low valent cations. For example, here, if you see this is the titanium oxide. In titanium oxide, titanium is in here, it is the Ti3+. So that is the low valent ion. Or we have the different oxygen vacancies. So if you have a pure material, if you create the defect, sometime material will become responsive. So that is the advantage of the defect formation. Application, there are many applications of the photocatalyst, for example, solar to chemical energy conversion, water and air purification, hydrogen and chemical fuel production. Okay, the performance of photocatalyst depends on several parameters. For example, the concentration, the mass, light intensity, wavelength of light, pH, temperature, nature of photocatalyst, particle size, surface area, adsorption nature, concentration of the substrate and all. So materials modification have been designed to improve it. For example, light harvesting and photon capture, how we can design a material that can harvest the light as much as possible, and in the charge separation and the mass transfer. And the photocatalytic materials must possess outstanding properties. So for example, these properties, better surface area, as you know, for catalysis, the material should have a high surface area, perfect chemical resistance, reduction in the permeability to corrosive environment, better anti-corrosion properties, optical clarity, increase in modulus, thermal stability. These are some of the other characteristics that the photocatalyst should have. So these are some of the application you can see here, that that nowadays we are using the photocatalytic material for many applications. So I will talk here in general, not the specific one. For example, the energy production. So nowadays the photocatalysts can be used for various applications. As Professor Isao has already told you that about the hydrogen production and many chemical conversions. So it can be used for various energy related issues. Okay, for water splitting or hydrogen production and all. Okay, and moving further, so you can see here there are many applications here. Solar H2 production here, that we're using different methods here. We can do the energy production, for example, the photocatalytic or photoelectrochemical or photovoltaic electrochemical. So there are many ways that hydrogen production by water splitting or other ways it can be done. Photocatalytic degradation of organic pollutant, that is another field. And if you search about the photocatalysis, you'll find that majority of the articles is reporting the photocatalytic degradation of organic pollutant. So that is the another approach or another application of the photocatalysis. removal of inorganic pollutants from wastewater. So this is another field where we're targeting the inorganic pollutant removal from the wastewater. So if you'll see here, as I've told you before, that removal of different metals can be done using this this technique. So the arsenic, cadmium, lead, and all, they're highly toxic, and they're found in the water. So these materials can be very easily precipitated out using the photocatalytic approach. So heavy metals, for example, you can see here, for example, chromium exists in the aquatic environment mainly in two oxidation state, this and this. So chromium 6 species are known to be carcinogenic and toxic, whereas chromium 3 is less toxic, can be readily precipitated out of solution in the form of this one. So using the photocatalysis, this approach you can see here, this is your photocatalysis using the light here. If you irradiate it, so it can be precipitated out. So using the same concept here, that you can generate the hole and electron, and this can be utilized for the removal of the inorganic materials or inorganic pollutants that are found in the different water bodies. In the same way, removal of different cyanides can be done here using the similar approach. Then water disinfection and purification, we can do the water disinfection. If the water, there are many microorganisms are there, so it can be purified easily using the same the photocatalytic approach here. So you can see here, this is the photocatalyst. And here what happened, there's if you irradiate, there's formation of electron and hole, and then formation of these the free radicals. So they can destroy the different the bacteria or viruses or other microorganisms that are present in the water. And another application is photocatalytic self-cleaning glasses. So this is another, is not new, but it has already started, that we have self-cleaning glasses. So now we have the very fine coating that can be coated on the glasses, and it will work automatically. No need to, clean automatically. If you coat it here, if the sunlight will come, and in the environment there is a moisture, and the photocatalytic reaction will take place automatically, and you will get a clean glass. So we have the self-cleaning glasses in the market nowadays. Then photocatalytic air purification. So this is another the application now. Very recently, I think some of the Japanese companies has already started, especially the Toshiba, the photocatalytic air purification air conditioners. So they have some device there, and then the air can be cleaned automatically. Then photocatalytic decomposition and removal of oil spills. We are using the photocatalytic material for the oil spill in the sea and the oceans and all. So using the same principle, that is the hole formation, electron, and then the formation of the free radicals. Photocatalytic paints. So this is another revolution of the photocatalysis. In the market now, we have the photocatalytic paints. So you can paint the building from inside and outside. When there is a light, the photocatalytic reaction will take place automatically. So that is another very big application of the photocatalysis, that is the photocatalytic paints, and it is already available in the market. Photocatalytic antibacterial disinfection. So this is another thing, photocatalytic antibacterial. As I've told you before, that currently we are working on this photocatalytic antibacterial. I'm sure that everyone knows about the antibacterial disinfection. So using the same principle here, we can use the photocatalytic antibacterial disinfection. So what happened if we use the antibacterial, some of the cations or the Roche species, the superoxide radical and all, it will be formed, and it will destroy the microorganisms. Then the last one is the photocatalytic chemical synthesis and or conversion. So using the same concept, we can synthesize several chemicals, okay, or convert one chemical to another chemical using the same principle here, and the principle will remain same. The fundamental will remain either the reduction or oxidation. So by using the different method, we can synthesize the different the chemicals. So if you see this slide here, this is the overall the conclusion of the photocatalysis, and it's very simple here. We have the photocatalyst, you can excite, and then you'll get the electron, the hole and electron, and then different reactions the different places it can take place, and then you can see the water splitting, CO2 reduction, N2 fixation, organic synthesis, degradation, and this achieved by doping or many method, and then dye-sensitization. These are different methods here. And you can see here, these are done by band gap engineering and all. So this is the overall conclusion for this one. And then this slide again give you the application of the photocatalysis. You can see we have the many application of the photocatalysis. Okay, so I have not discussed any of my specific work here. So if someone is interested, you can go to my Google Scholar or Scopus, and you can find the my articles, and you can read. Or if you want to discuss anything, you are welcome. You can email me. Okay, yeah. So I would like to thanks the UBD for providing me the opportunity to work in this field, and also I'm thankful to Dr. Lucia Noati for inviting for her kind invitation. At the end, I would like to thank the organizing committee members of the world-class professor program. So this is my small group where my PhD students, master and PhD students are working. So at the end, I would like to say that science is a nation or world in itself. So we should work together in interdisciplinary and multidisciplinary fields to understand, explore, and achieve our common goal. Whatever we do, we should do with regard, sincerity, full confidence, trust, and for our own satisfaction, not for others. So you're welcome for collaboration if you're interested. Thank you.
Thank you very much, Prof. Mansur, especially for your last words. It's very inspiring. So, thank you, Prof. Mansur. Prof. Mansur, once again, for your presentation about nanomaterials for photocatalysis. If any of you have any question for Prof. Mansur, please put it in the comment section or raise your hand during the Q&A session. Okay, for the last, we will have a presentation delivered by Dr. Aussie from the Research Center for Chemistry, National Research and Innovation Agency, Indonesia, or BRIN. Dr. Aussie is a skilled researcher specializing in the functionalization and structuring of metal oxide-based nanomaterials for application in photocatalysis. Her expertise lies in developing innovative photocatalytic for environmental challenges, including organic wastewater treatment, antibacterial application, and the conversion of CO2 gas into valuable compounds with added benefit. Good morning, Dr. Rosie. Okay, maybe we will wait for a while for Dr. Rosie to come back to the room. Added benefit. Good.
Good morning, Dr. Aussie. Good morning, Dr. Aussie.
Okay, while we wait for this one is Dr. Aussie. Good morning, Dr. Aussie.
Hello. Good morning, Dr. Aussie.
Good morning, Dr. Lucy. I'm sorry. Yeah, I have a problem with it. Please.
Okay, Dr. Rossi, I have just read your short summary, and now it is your time to give the presentation for the last session. Okay, Dr. Rossi, you can start. You have about 30 minutes. Thank you. Dr. Rosi, is there any problem with the share screen?
Yeah, it's okay. I will start. Okay. Good morning, everyone. Thank you very much for Dr. Lucy to invite me to share my knowledge here. Hi, everyone. My name is Osi Arutanti from Photochemistry and Catalyst Research Group, Research Center for Chemistry, BRIN. Today, I would like to share to you about the development of titanium dioxide-based photocatalyst material from natural mineral Indonesia. Yeah, this is my briefly CV, which has been recorded by Dr. Rizky and before, and I will conclude about my expertise related to the development of immobilized titanium dioxide photocatalyst, and then functionalized aerostructure metal oxide for photocatalyst and photocatalysis application, and the last one is dispersion nanomaterial. Okay, now I will start from what's the problem is. We start from the global issue. We know that the development of human and then technology, it will give the negative impact into our environment, such as soil pollution, water pollution, and then air pollution. Here we will focus to the air pollution. So who give the bigger contributor to our air pollution? One of them is the use of fossil fuel for transportation, and from the industry, and also the domestic activity. In Indonesia, we do not only have the fossil fuel as the electricity resources, but also we have geothermal and hydrothermal. This is one of kind the same plant in our country, geothermal in Kamojang in West Java and hydrothermal Cirata in West Java. We also, along with the development of science and technology, is there another clear energy which can be used for our activity? It's called hydrogen, due to the clean, efficient, and abundant. This is the several of methods to produce the hydrogen, such as steam methane reforming, coal gasification, partial oxidation of hydrocarbon, biomass gasification, electrolysis, thermochemical, and photocatalytic. But here, I will focus to the photocatalytic. So what is it, photocatalytic? Yeah, as previous mentioned before, photocatalytic is one of the advanced oxidation process which can be defined as acceleration of reaction in the presence of photon and catalyst. So that's why we choose the photocatalyst method to produce hydrogen. Because we believe that this method is relatively cost effective and then environment, and also we can use solar energy to activate our catalyst. This is the mechanism photocatalytic for hydrogen production. In simply, when the catalyst absorbs the photon, will be produced the pairs of electron and hole, and then the generated holes in the valence band will oxidize water, become to O2 and H+, while the generated electron in the conduction band will reduction the H+ become H2. And then what the kind of resources material which can be used to produce the photocatalyst, especially in Indonesia? Is there typical of resources material such as silicate mineral, sulfide minerals, borate mineral, and metal oxide. This is, for example, for the silicate mineral, there are zeolite, monocloride, diatomite, kaolin, etc. For zeolite, we can farm from the volcanic. The advantage of the zeolite is due to the pore structure. they have a lot of pore structure, and then also zeolite has a good electron donor and acceptor. We can find the zeolite in Indonesia, in Lampung, West Java, Java, Nusa Tenggara Timur, and Sulawesi. And then the second one is sulfide mineral. For the sulfide mineral, for example, chalcopyrite and pyrite and sphalerite. The use of sulfide mineral due to the high absorber material. They also has the characteristic for strong magnetic material and heavy metal absorption. It's suitable to be used as a photocatalyst to water treatment. And we can find the sulfide material in Indonesia, especially in Sumba Island. And then the last one is metal oxide. For example, hematite, magnetite, and ilmenite. Here, I will focus to ilmenite. Ilmenite is one of side product from the tin mining industry, and the composition of TiO2 in ilmenite usually around 60 to 80%, depends on the typical of ilmenite. We can use metal oxide as photocatalyst material due to the characteristics such as low toxicity, light absorption, recyclability, and also resistance. And yeah, ilmenite in Indonesia is abundant. And then this is the typical of metal oxide, which can be used as the photocatalytic material. I will divide it into two groups. The first one is the common photocatalyst, which usually used in Indonesia, such as zinc oxide, Fe, and titanium dioxide. And the second one is tungsten oxide. Tungsten oxide usually common photocatalyst in research worldwide. Why we use the red one? Why we use we use the red line? Because compared to tungsten oxide, titanium dioxide is relatively easy to find in Indonesia and relatively cost life, and we have a lot of resources from TiO2. However, yes, and this is another perspective of the use of titanium dioxide for paper, plastic, paint coating, and etc. And yeah, we can start from the titanium dioxide. So why titanium dioxide? When I come back to Indonesia, I start to thinking about what the possibility material which can be developed if I want to make the photocatalytic technology can be applied in Indonesia. So I think is titanium dioxide is the feasible one. In the worldwide, it can be seen that from the CGR number, the value of titanium dioxide from 2020 and 2028 around 7 to 8%. It means that the demand of titanium dioxide is continuously increased. And the most country to use titanium dioxide is Asia Pacific. This is another application of titanium dioxide. And in 2022, European Commission announced that titanium is starting to be classified as critical raw material. Why? Because as we know that when the demand increases, so the availability will be decreased, resulting in the higher selling prices. This is the titanium dioxide based on the Ministry of Trade Indonesia 2022. Here we can see that the number of export titanium dioxide is higher than import. The number of export titanium is lower than the total number of import titanium. In fact, we have a lot of ilmenite in Indonesia, and ilmenite as byproduct of tin mining activity has not been optimally processed in our country. Usually, we produce 4,000 tons of ilmenite per year. Based on this condition, our government issued a regulation to prohibit export the ilmenite before with the ilmenite become to another material. This is the way to recover titanium dioxide from ilmenite. Is there 3-way step. The first is pretreatment, and then the second one is leaching, and then hydrometallurgical. For pretreatment, is there oxidation and reduction process, usually by thermal reduction at high temperature or additional carbon material to remove oxide iron. And then the second one is mechanical activation. It can be used by grinding, milling to enhance the specific surface area, changing the crystal structure. And then the hydrothermal conversion. And for the leaching process, it can be used the sulfuric acid and chloride acid. Okay. And the activity or the optimum condition is depend on the particle size of ilmenite, time temperature for leaching process, and the ratio concentration between the acid and the ilmenite. This is by leaching by oxalic acid, and the third one is the hydrothermalogical by caustic leaching. This is the recovery titanium dioxide process, which common use. For the first by solid state reaction, this is the complicated, most complicated process, and the second one is the batcher method. Usually, this method is used by industrial, and also the chloride method. And this is the newest method to recover titanium dioxide from ilmenite by microwave. What the difference between the conventional method? Here, they use the natrium carbonate and ilmenite, and then they use a microwave process to reduce the temperature process and time process. And then by this process, it can be found that the both of time and temperature process can be more decreased. Here we can use temperature below than 1000 degrees Celsius, while if we use the conventional method, we use the temperature above the 1500 degrees Celsius. And here we only use the time process only from 30 minutes to 3 hours, but by the conventional method, usually we use above of 5 hours, longer than 4 hours. So how about the challenge and potential the use of titanium dioxide as photocatalyst material in Indonesia? First, based on the basic science, during the 10th year, we only found the 74 publication related to the 28 article and 72% conference proceeding, and almost of the published paper is only the use of titanium dioxide for water treatment, not for hydrogen production. And then the second one is we have the conventional technology, but the technology is not yet suitable for the industrial market. So that's why we need to develop more and more the method to recover titanium dioxide from ilmenite to get the optimum process. And then the opportunity is the ilmenite in Indonesia is the second most abundant byproduct after quartz, around 4,000 tons per year. And then due to the high demand, and then of course, by develop this technology, opening up further opportunity to cooperation as well as the process product. Yeah, the treatment is the existing technology can produce titanium dioxide with high purity. Okay, that's all the challenge and the potential of development of titanium dioxide from recovery from the ilmenite. Next, I will show you the example, the use of titanium dioxide based photocatalyst for hydrogen production. A lot of technology based on titanium dioxide, which has been used to produce the hydrogen production. But here I will show you only 2 paper-related titanium dioxide-based photocatalysts for hydrogen production. First is potentially reduce NE-oriented IO2 to produce hydrogen production from water solution. Why I choose this paper? Because they want to show us is how we can create the photocatalyst material without the precious metal, but we can get the high hydrogen production. Here, the first process for the first graph, this is the XRD peak related to, they try to create the composite of Ne and TiO2 biological gel method. For the first one, they only annealing the particle at 450 degrees Celsius in the air, and we can found that from the XRD peak, the only titanium dioxide anatase, and we can found NEO peak. However, when they calcium the catalyst at 450 degrees Celsius under H2N argon gas, you can see that they also produce the titanium dioxide, but the peak of NEO shift become Ne. Here we found the small of NEO, but almost NEO from the figure A shift become Ne peak. How about from the morphological? From morphological, this is for pure titanium dioxide. This is for calcium titanium dioxide, and this is for reduced TiO2 Ne. Here we can see from the same image that the additional Ne didn't change the morphology significantly, only change the surface area from 24 to 79, but the reduced process didn't affect it to the morphology and the surface area of the particle. Here we can see from the Raman spectra, this is for the calcium catalyst. We can see at the peak of titanium dioxide, almost peak by adding the number of Ne almost similar. However, the reduced process make the peak of titanium dioxide shift. It can be assumed that the presence of oxygen vacancy due to the reduced process resulted in the shifted of peak of titanium dioxide. This is for UV-Vis DRS spectra. By adding NEO into the composite of TiO2 NEO, the wavelength is the energy band gap also decreased, a little bit decreased. This is for the pure NEO, and this is for the pure TiO2. So it can we can make sure that the change of energy band gap is due to the presence of NEO and titanium dioxide. But here they cannot show the energy band gap for reduced composite due to the band gap is too small. Okay, and how about the photocatalytic activity? Here they show the interesting result. By increase the NEO number, the photocatalytic activity also increased, but only slightly increased. However, when they use the reduced catalyst, the hydrogen production drastically increased. But here the optimum condition was 1 ratio, because the excess of Ne resulted in the decreasing of hydrogen production. Here we assume that the excess of oxygen vacancy can reduce hydrogen production due to the presence of electron-hole recombination. And the second one, I choose this paper, Engineering Defect of TiO2, to produce the hydrogen production by Zeng et al., and has been published and applied catalyst B environment. Here they show us how to produce free metal catalyst with the high photocatalytic activity. here they use TiO2 P25, and then they use sodium boroxide as the reduction agent. If in the previous paper they use hydrogen gas as the reduction agent, here they use only sodium boroxide. The hard-time image show that after reduction process, they get the disorder lattice fringe, or it was due to the defect crystal. And how about from the Raman process? The Raman process or the Raman analysis result also similar with the previous one. Titanium dioxide peak little bit shift due to the reduction process by increase the concentration of sodium boroxide. And also this is from the UV-vis DRS spectra. The wavelength increase from the 400 to 80 degrees Celsius, and this is the energy band gap. The energy band gap little bit decreased from 3.37 to down to 3.14 electron volt. And how about the photocatalytic activity? We can also see that by increasing the sodium boroxide concentration, the hydrogen production is also increased. And 0.5 is the optimum condition to produce hydrogen production with the purity above of 99%. And then when we added more the sodium boroxide, the hydrogen production decreased. It was due to the excessive of oxygen vacancy from migrate into the bulk structure and act as a recombination center. So that's why in this case, we should find the optimum condition for the number of oxygen vacancy to get the optimum hydrogen production. Okay, that's all. Okay, for the conclusion, yeah, we believe that in Indonesia, the development of titanium-based photocatalyst derived from ilmenite as a sustainable technology is highly feasible, and the design and development of method to recover titanium dioxide from ilmenite are still widely open. In the process, recovery titanium dioxide from ilmenite, the pretreatment process and acid leaching play an important role. And the processing method to recover TiO2 from ilmenite using a short and efficient acid treatment is highly needed to meet demands of the industry. And related to the hydrogen production, we know that photogenerated charge separation, prevention of water splitting, vaporization, and the last one, the photocatalytic performance could enhance by increasing the oxygen vacancy. That's all my presentation. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you very much, Dr. Rossi, for your presentation regarding development of titanium oxide-based photocatalyst material from natural mineral in Indonesia. Okay, we have heard all of the presentation, and now it is time for the Q&A session. So if anyone have any question for either of speakers, you can raise your hand and we will give you time to ask the question directly. Anyone? Okay, Mr. Abdul Wafi, you can turn on your camera and ask the question. Please be specific to whom you regard your question to.
Okay.
Okay.
Thank you, Pak Rizky. My name is Abdul Wafi. I'm from BRIN, actually. It was a beautiful presentation from three of speakers. I'm also working on photocatalysis, actually, just on titanium dioxide. So from the my perspective is really insightful. So my question first for the Professor Yoshida, it's about the I'm curious about the thermal catalysis. So as in the presentation, Professor mentioned he used the X-ray lamp, if I'm correct. So how about another devices, maybe for the thermal treatment, other than for the this X-ray lamp, probably. So the second one for the Professor Mansuk, if I'm correct, I heard from your presentation regarding the photo antioxidant. If correctly, I'm curious about this because I'm working also on the photo antibacterial, but photo antioxidant. I'm really interested about it. So probably you may give us some example on the current trend in this area. Probably this. Thank you, Pak Rizky.
Thank you, Pak Abdul Rafi, for your interesting questions.
Okay.
We will start for Prof. Yoshida to
Okay.
answer
So,
Mr. Wafi question.
I'm sorry. Please repeat the question only.
Okay, Mr. Abdul Wafi asked about regarding thermal catalysis. Previously, from your slide, he said that you use some device, XLAM, and he asked about how about another device to do the analysis? Is there any possible devices? I think that's the question. Mr. Wafi, if I'm
Yes.
wrong, you can.
Correct. Exactly.
Mm-hmm. So I still cannot catch the meaning. So the photothermal process, then
Yes.
sorry, what is the question?
Probably there is another devices other than the lamp for the thermal treatment for the catalysis. Probably, for example, by a hot plate or something. I don't know exactly. For another devices for the thermal source other than lamps. Yes.
Okay. In this case, the heat source is okay. We always the electron fan heater like the usual metal heater. Anyway, to make the heat, we usually use the electricity, but it's not so good for the future. So that we want to try the use of the photo energy, I mean the sunlight. So for the experiments, of course, we can use many kind of the tools to heat the catalyst, but the result is the same. Only the temperature determine the catalytic activity in case of the usual catalyst. So that the point is the photo energy can be converted directly on the active site of the catalyst. In this case, metal nanoparticles. Is it okay?
So if you use like a solar light, in my perspective, we use both a photo and a thermal catalysis because there's also a light there, if I'm correct like this.
Mm-hmm.
So it's possible using the solar light also.
Yeah. Of course, yes.
So in this case, we use both photo catalysis and thermal catalysis. All right.
Mm-hmm. Okay. So in case of the photocatalyst, we usually use the semiconductor such as titanium oxide. In this case, the light excites the electrons in the semiconductor, and then we use the electron and the hole. But the photothermal system is quite different from this photocatalytic system because the light energy is absorbed by metal nanoparticle directly, and then the energy is immediately is converted to the heat.
Oh, yes, yes, yes.
Mm.
Okay, okay. Got it.
The light source, we usually use the lamp for the in the laboratory, but of course we can use the solar light. Then now when probably it's better to concentrate by the lens to the catalyst.
Yeah, yeah. Okay, okay. Thank you very much, Professor.
Thank you.
Thank you for your answer, Prof. Yoshida. The next to Prof. Mansuf.
Yeah. You listen me? Is it clear?
Yes.
Yeah. I think what I remember is question that he want to know about the photo antioxidant studies.
Yes, yes.
Yeah. As I told that we have, if you see the antioxidant, so for antioxidant, there are a lot of natural product that is used for the antioxidant. But so what we do here, we modified that work and we have come up with the thing that is the photo antioxidant. Okay, so here what we do, we use the the photocatalyst and we check the antioxidant activities in the dark and in the light. For example, let me just share something with you here if you want. I'm not sure whether you have come across with some of my article or not here. Maybe then things will be easier to understand. You see this one, this article?
Yeah, it's clear.
So this is actually the review article. Okay. So green synthesized serum oxide nanoparticle for photo catalytic, antibacterial, antioxidant, and cytotoxic activities. Okay. So using this concept, we have modified this work and this work, it was published in the Biomaterial Science here. Green synthesis of serum oxide, and it was doped with the co-doped with the zirconium and tin for photo antioxidant and anti-biofilm activities. So here, what we did here, if you see this work here, I want to show actually the mechanism. I don't have in the slide here, so I quickly have opened the article here so that you can see here. So you can see here the response in the dark and light. Dark and light. If you do the antioxidant only using the material, it is showing this much. But if you have the light, this is the light response. So this is why we call it photo antioxidant. So if you use the light, you can see the mechanism that we have proposed here in the dark and in the light. If you put the light, what will happen? The more and more, sorry, loss will be formed, and it will affect the photo antioxidant studies. This is another study here. This is in this case we used the tin oxide, and it was co-doped with the cobalt and nickel, and we did the photo antioxidant studies using this. I'll say the same or similar the principle, and we have proposed the mechanism and all. So basically, if you see here, this is the under the here the dark and light. This reaction was performed under the dark, and here we irradiated with the light. You can see the response. The response is different. So based on that, we have proposed this mechanism here. So this reaction, it is in the dark. This is in the light. So there's a light response. If you put the light, there will be enhancement. So that's why we call it photo antioxidant. Hope things will be clear.
Okay,
Yeah.
thank you.
Thank you.
Yeah.
Thank you for your answer, Prof. Mansur.
Yeah. So
And then we
try
still
to
have
try
a
to
lot
go
of
through the try to go through the articles,
from
and if you have still any confusion, drop me an email.
Okay. Okay, we will continue for the next question. We still have a lot of question from the chat box. So maybe we first start for Dr. Osi. I will quote the question. This one. For Dr. Osi, you can find the question from the chat box, this one. What is the difference between dye degradation mechanism using only absorbance process and using photocatalysis under irradiation process?
Okay, thank you very much for the question. Yeah, if the absorbent process, we use the absorbent material to absorb the pollutant organic. However, the disadvantage from the absorbent is they has the limited to absorb the pollutant organic. So in some value of pollutant organic, the material will be fulfilled to pollutant organic. So we need to we can use, or for some material we cannot use anymore. We need to reuse the particle to evaporate the pollutant on the photocatalyst surface, on the absorbent surface, and then we can use again. However, for the photocatalyst, the pollutant degraded not to be absorbed. So we try to decompose the pollutant organic, for example, rhodamine B, and then we degrade the chain of rhodamine B become to CO2 and H2O. So even we reuse the photocatalyst again and again, the activity of photocatalytic is not bit more decreased because the photocatalyst didn't absorb the pollutant organic. We decompose, not the photocatalyst is decompose the pollutant organic, not to absorb the pollutant organic. Is it clear enough?
Yeah,
Bu Lucy, you have any response?
it's quite enough.
Okay, thank you, Dr. Rossi, for your answer. The next one is for Prof. Mansur.
Yeah.
Which active sites will be better for enhancing the photocatalytic chemical reaction? Metal single atom or metal nanocluster or mixture of them? Prof. Mansur?
Yeah. So actually, when I say this question, so if you see for the photocatalysis, so for photocatalysis in general, we need the semiconductors. We need the semiconductor. Okay, because if you not use the semiconductor, you cannot generate or you cannot create the hole and electron. That is the main thing here. So, and the question is that which active sites will be better for enhancing photocatalytic chemical reaction? So, I mean, the question is very general, so it's very difficult to say what he want to ask. The second part, metal single atom or metal nanoclusters or mixture of them. So here again, just now I told you that for photocatalysis, what we need is semiconductor. We need the, sometimes what we do, as I told, and during my talk, I told you that we use the metal or non-metals either to dop the semiconductors or to modify the surface of that one. So using the single metal or nanocluster, we can modify the semiconductors, but we cannot perform the photocatalysis using only the metal. So if whosoever asked the question, if they can put me the clear question, the first part especially, which active site will be better for enhancing the photocatalytic chemical reaction? Now here the thing is that what type of reaction you want to do, because using the photocatalysis, either the reduction reaction or the oxidation reaction can be done. So it depends. Accordingly, you have to choose the material based on your application.
Yeah, thank you, Prof. Mansur. The next one is for Prof. Yoshida. How can we combine photocatalysis with other technologies such as electrocatalysis to achieve more efficient and versatile energy conversion and storage?
Okay. As you know, the history of the photocatalysis start from the electrochemistry. So in that case, the photoanode is the titanium oxide, and the counterpart is the platinum. It's a typical electrocatalysis. So that our study of the photocatalysis can be applied to the photoelectrocatalytic reaction system in principle. So probably in future we will use this system for the application for our life. But for the study, it's better to use the photocatalysis directly because we can make it easily, modify easily compared to the photoanode. Maybe you know the making the photoanode is a little bit tough. So so that the output will be the photo system. Maybe, but for the researcher, I think the photocatalytic powder, photocatalysis is enough. Is it okay?
Okay, it's clear, Prof. Yoshida. So the next questions, I also these questions toward to you about is it possible to produce hydrogen from methane using photocatalysis without carbon dioxide emission? Is it possible?
Yes, yes. I introduced two types of reaction in hot summer reforming. One is carbon methane plus water gives the carbon dioxide and the hydrogen. But another is a reaction between the methane and the carbon dioxide to give the carbon monoxide and hydrogen. In this system, the product is hydrogen and carbon monoxide. So it's answer. Okay.
It is clear, Mrs. Sisi? Thank you, Prof. Yoshida. The next we have a question for Dr. Rossi. What is the purpose of the hydrothermal process in pretreatment enriching of ilmenites? Also, ilmenite has varying concentration in some areas in Indonesia. Okay, Dr. Rossi, did you find the question?
Okay. Okay, thank you very much. Yeah, I can read this one. What is the purpose of the hydrothermal process and leaching process? The process is to reach or to separate the another material with the IO2. So by leaching process, for example, with chloride acid or sulfate acid, the sulfate will be dilute another material content in the ilmenite, except the titanium dioxide. So we will get the particle of titanium dioxide, and we also get the solution of metal sulfate. That is the function of leaching process. And then will impurities affect the structure of the IO2 produced? Yes, of course. Usually, titanium dioxide from ilmenite, the structure is brittle. And what the impurities we want to need is depend on our need. If you want to get the pure titanium dioxide, so we should optimize the condition. Usually, the most important things is the concentration of chloride acid or leaching process to get the more purity of titanium dioxide. But in our laboratory, we are trying to optimize the all condition from each stage to understand how the effect of impurity on titanium dioxide characteristics. Because we know that the impurity of titanium dioxide could enhance the photocatalytic activity, right? Because by the impurity, the presence of impurity, we can reduce the band gap energy. We also we can in this avoid the electron hole recombination. So in our lab, we try to study it step by step.
Okay, thank you, Dr. Usi, for your answer. The next one, we have a question for Prof. Mansuf. In Kalimantan, we have acid mine drainage pond from coal mining in large quantity, and for now, they just using many coagulant to neutralize the pH and to reduce some contaminant. But in the other side, using coagulant make another problem because produce many of sludge. And my question is, in the term to reduce the amount of sludge, can we combine the photocatalysis treatment for acid mine drainage treatment and also for enhanced hydrogen production? Prof. Mansur?
Yeah, actually, there are two questions. First, before that, there's another question. To study the lifetime of a photocatalyst materials, multiple runs are performed with the same catalytic material. What is the best way to filter and reuse the catalyst for the dye? Okay, so I'll answer this question. Here, I mean, this is a big challenge for the photocatalysis, the catalysis. If you are dispersing the material in the waste or in any liquid, so in that case, what we need to do, we have to filter it out. So we have to find a proper way so that you can filter out. Another way that you can develop a reactor where the catalyst is coated on any surface. So in that case, what will happen? The photoreaction will take place and the catalyst will remain on the surface. So we have developed some reactors on which the catalyst will remain there on this. So it will not mix up. So then no question of the separation or filtering. But if you are dispersing the photocatalyst in the system, what will happen? We have to find it. I mean, what we do here in my university, we have the centrifuge machines. So we use the centrifuge. So with using the centrifuge, we can just depending on the material and all, the particle size and all. So maybe about 3,000 or 4,000 or 5,000 RPM we separate. So there are two ways. One way, if you have the reactor where the material can be coated, we can use that one. In that case, there is no need of any filtration or separation. The material is already out. Second thing is that if you're dispersing, then either you can use as I told you that what we do here, we use the centrifuge machine. Okay, we put everything and just centrifuge and the material will be out. Okay, or if you don't have, you try the using any filtration, suitable filtration. Any type of frit, it will depend on the particle size and all. So that is the first answer. The second one regarding the Kalimantan, we have acid mine drainage and all. So now the question is that in terms of reduce the amount of sludge, can we combine photocatalyst treatment for the acid mine drainage? Therefore, as I've told you that photocatalyst is also a very hot topic. Okay, and it is expanding. If you'll go before 10 years, 15 years, 20 years, people think that the photocatalysis means just degrading the dye. I'm talking about the academic research. So majority of the people think that it's just the degradation of the dye, but it's not like that. We are expanding. Okay, so if you see today, we have the photocatalytic paints, we have the photocatalytic tiles, many applications are there. So based on the location, the problem that you're discussing here, the researchers or scientists, those who are there, they can see that first we need to see the type of the waste or sludge that is coming out, how it can be handled. That is important because here again the thing is that, for example, if you have a reactor, so whether the sludge can be passed with the reactor or not, so it can flow with the reactor or not. So there's so many factors will be there. So those who are there, those who are working on the photocatalysis, either Dr. Lucy or Dr. OC and all, so you can see that because without seeing the waste or the sludge is very difficult to suggest. Okay, but I'm sure that if will work, it is possible. It can be done.
Okay, thank you, Prof. Mansur. Actually, we have one more question for Prof. Mansur. Can you find it in the?
So the next one is photocatalysts are exposed to harsh reaction conditions, including high temperature, intense light, reactive species, and all over time. These conditions can degrade catalyst structure and performance, how to control the stability of the photocatalyst, and how lifespan and all this is talking about. Then in the real world condition, variation in sunlight intensity correct. You see that during my talk, I told you that the photo corrosion, that is the main challenge that the photocatalyst material get the face. So if you radiate with the light, what will happen? Light is there and the material will get photo corroded. That is the one problem. Okay, and you can say it is related with the stability. So of course, if you take any material, for example, if you are using a battery, battery will not remain same, or it will not work from what you have bought first day till the last day. So its efficiency will decrease. It will not remain same. The same thing with the photocatalyst also. If you're using the photocatalytic material, it will not respond always, in the same way. So for the first run or for the first few months, but if you keep on using, its efficiency will keep on decreasing. So it's a challenge. It's a challenge for all the system, not only the photocatalytic materials. I told about the batteries, for example. So batteries will not remain same for after 6 months or 1 year. Its performance will keep on decreasing. So same thing with the photocatalyst also. So, but if you see, if you keep your eyes on the latest publication, new reactors are coming that we can regenerate the photocatalyst. We can regenerate. So once it will be when you're using, if its efficiency is decreasing, so by different treatments, some by acid treatment or other treatment, we can regenerate the photocatalyst. In that way, its stability, or you can say the efficiency, can be maintained.
Okay, thank you, Prof. Mansur. And actually, we still have a lot of questions from the YouTube channel. I will post some of them. The question is for Dr. Osi. What are some of the challenges you've encountered during the process of extracting and synthesizing titanium oxide from the natural mineral, and how have you addressed these challenges to optimize the photocatalyst performance?
Thank you very much for the questions. Yes, there are really challenges to produce the titanium dioxide, the pure titanium dioxide, especially how, like the question before, how to separate the titanium dioxide with Fe. And then this is also tricky. After leaching process, maybe we can get the 80% titanium dioxide, and then when we try to annealing the product to enhance the crystallinity, and then the oxidation process occur, and the purity of titanium dioxide decrease and the Fe that increase. So this is really challenging. For now, until now, we try to optimize because the most very important role is the leaching process. So we really try to optimize in the leaching process regarding to the temperature that we can use during the leaching process, and also the concentration of leaching process.
Thank you, Dr. Osi. Maybe the last question is for Prof. Yoshida. In terms of sustainability, what are some potential challenges and opportunities associated with the large-scale implementation of catalytic methane conversion for hydrogen production?
Okay, the sustainability, the main very important point is we must change the energy source from the fossil fuels to the solar energy. The fossil fuel mean the oils, gas, and gas mean the methane also, and the coal. In these materials always gives the carbon dioxide into the atmosphere, so that we must change to the solar energy. In this case, I give the talk related to the methane conversion. If we use the methane from the underground, its come to the carbon dioxide finally. So that first we must stop to use the natural gas first. And methane can be obtained the usual biomass when we convert the biomass to other chemicals. Methane also produced. This is available source for the energy, hydrogen energy. In that case, we must use the photon energy even to convert the methane, so that for the sustainable society, the methane conversion is still important part, only a part of our energy issues. It is not solved the all, but we must develop many systems to produce energy from sunlight. Then the methane conversion is one of them. So in this case, the question is maybe the scale up is necessary. And now we use a very small reactor in the laboratory. But if we extend the surface and the area of the reactor, of course, we can use the solar light efficiently. So these kind of the reactor also very important to receive the sunlight directly. And we found also the sunlight should be concentrated to the one point. I mean, the high concentration of solar light gives higher temperature, so that it's very important. So that we use some lens to concentrate to the catalyst part. In such way, we will use the solar light correctly. This is my answer.
Okay, thank you, Prof. Yoshida. Okay, everyone, our time for discussion is over. Thank you very much for the question and answer from Prof. Yoshida, Prof. Mansuf, and Dr. Rossi. I hope our discussion will bring benefit for us, for our institution, and for our country. That will be all from me. My apologies for any mistake. I will give it back to Mrs. Rizka as the MC.
Thank you very much, Mr. Ginting, and many thanks for all of guest speaker and participant today. And the presentation slides of the presenter will be available in the comment box. Please check regularly. Ladies and gentlemen, we have reached the end of our program today. Before we'll finish it, we will take a picture once again. Please turn on your camera and use the virtual background that's available in the comment box. Please turn on your camera for all the participants. Okay, same like before. We will take a picture 3 times. We'll start from the first slide. 1, 2, 3. Okay, the second slide. 1, 2, 3. Okay, the last slide. 1, 2, 3. Okay, thank you, everyone. We move for giving appreciation in the form of certificate to our special guest. First certificate is for Professor Hiso Yoshida. And then the second certificate is for Professor Muhammad Mansuk Khan. And then the last one is for Dr. Osi Arutanti. Okay, many thanks for our speakers. who have willing been to share their knowledge and experience to all of us. That is all from me. I'm sorry if there are any shortcomings during the event, and see you at the World Class Professor Program series next week. Wassalamualaikum warahmatullahi wabarakatuh. Good afternoon, everyone.
Waalaikumsalam
everyone.
warahmatullahi wabarakatuh.
Good afternoon, everyone.
Thank you, Prof.
Arigatou gozaimasu, Sensei.
Terima kasih Mbak Usi.
Domo arigatou
Makasih, Mas
gozaimasu,
Rizky.
Sensei. Domo arigatou gozaimasu, Sensei.
Makasih Bu Lucy.
Hai, hai. Thank you, Dr. Asi. Thank you very much, Prof. Mansub.
Yeah, you're welcome.
Tutup.